Okay, welcome to this week's lectures. I left you last time with a little simple problem really, just to give you some feel for timescales of the late stages of these evolution of stars. So here's another nice, pretty picture of one of these planetary nebulae. So you've got the shell of gas that's been ejected from the outer layers of the star. Still see the central star in here. In fact, this is a famous object. That's the Hubble picture, but you can see this object with binoculars. If you know where you're looking, it's actually quite close to the star Vega in the sky. So up in the evenings at the moment, called the Ring Nebula, for fairly obvious reasons. So how long does it take for that material to sort of travel a reasonable distance? And so for a reasonable distance, I'm just taking sort of 1 parsec as the distance to the next sort of star, if you like. Okay. And this material is expanding at sort of relatively moderate velocities for sort of astronomical things at about 10 kilometers per second. Okay. So just a simple time is distance over speed type of argument. So if we want to go 1 parsec, which is about 3 × 10⁻16 meters, and we're going at 10 kilometers per second, so let's change our speed into meters per second, then you get 3 × 10⁻12 seconds, which is about 10 to the 5 years. Okay. So in 10 to the 5 years time, this material will have dispersed quite a lot. In fact, after about 10,000 years, these nebulae fade so that you can't see them. So let's compare this sort of timescale of 10 to the 5 years to other things that we've met in the course already. So sort of typical main sequence lifetimes of stars are much longer than this. And so that's the kind of idea here, that these kind of processes that are re-injecting material, enriched material into the space between the stars at the end of a star's life, those processes are fairly short compared to the actual lifetime of stars. So you can see that this idea of sort of recycling material into new generations of stars can be a fairly quick turnover. Okay, so what are we looking at this week? Well, we're looking at, finally, this is the last of the sort of lectures now on sort of properties of stars. So we've seen in recent lectures that the mass of a star is absolutely vital, determines everything about the star, where it is on the main sequence, how long it stays there, and where it goes afterwards, and how, and what it ends up as. So I think we better make sure we can actually measure stellar masses so that we can, understand where all of this information comes from. So that was going to bring us to looking at binary systems of stars that I'll introduce in this lecture. We'll talk about Kepler's third law, which you may well have met in some guises before, but we're going to do it a bit more rigorously. And then we'll sort of get ready for the following lecture, where we sort of talk about sort of the real orbits of stars and introduce some of that terminology. Okay, so a fairly short first part just to introduce this topic. So, why can't we just determine the mass of a star from, taking a spectrum of the star, for instance? I mean, you can have a bit of a stab at it from sort of information in the line profile, but it's not very easy and it's not very accurate. So that's basically, if you've just got a single star sitting there by itself, it's quite difficult to infer the mass of the star just from studying the properties, if you like, of just the atmosphere of the star, which is where the spectra comes from. So if you want to measure the mass, you better find a property that the mass directly influences. So what does mass do? Well, it exerts gravity and it pulls other things around in the nearby. Okay. So that's the real way to determine mass, is to use the fact that mass determines the gravitational field around an object. And so, but even then, you need to put something else in that gravitational field for it to pull on. Otherwise, you're not going to see that gravitational influence. So luckily for us, well, luckily and unluckily, who knows. But most stars are actually in binary systems, so they come in pairs, and they can even come in multiple systems as well, where you've got 3 or 4 stars in a sort of stable system. So although I've been telling you that our sun is, is a very average star, the one thing that is not so average about it is that it is actually a single star and not a binary. So for stars like the sun, about 60% of stars like that are in binary systems, and 40% are like the sun and single. Okay. So, but it's the binary systems that allow us to measure the mass, as we should see. Okay, so before we get stuck into the sort of derivation of Kepler's law, third law, then let's introduce you a little bit to this topic. So the brightest star in the sky, Sirius, that we had when we mentioned a little bit when we talked about magnitudes. Very famous object. As the nights draw on in the winter, you'll see Sirius extremely bright in the sort of southwestern sky, so fairly low in the horizon. Okay, but with a reasonable telescope, you can see that there are actually 2 stars there. In fact, here's a picture taken by sort of fairly just an amateur astronomer, I think, where you can see that this is the bright star we see with the naked eye, but with a telescope you can see that there's another star just next to it there called Sirius B. And in fact, Sirius B is a white dwarf star, quite a famous example of a white dwarf. Whereas Sirius A is just a normal main sequence A-type star. So if the angular separation between these 2 objects is 11 arc seconds, and the distance to the system is 2.6 parsecs, what's the physical separation here? And in fact, I'd be good if you could put the answer in astronomical units, just to give you some kind of scale, and we can relate it to the solar system. So work out the separation in meters, but then convert to astronomical units. Okay, so if you have a quick go at that, and we'll come back after the break and get stuck into Kepler's third law.